Hi everyone, today I'm going to talk about our paper, Online Learning for Hierarchical Scheduling to Support Network Slicing in Cellular Networks. I'm Jianhan. This is a joint work with my supervisors, Professor Gustavo and Professor Sanjay. Let me first start with the general idea of network slicing. Basically, it's a hierarchical framework for resource allocation. The base station first maps users or say traffic flows into several slices. Then it partitions network resources, the bandwidth for example, into those virtual slices based on some allocation rule. This allocation typically happens in a slow timescale. At the same time, base station deploys flow-level schedulers within slices, which schedule users using resources allocated to each slice by the slice-level scheduler. This is fast timescale allocation, and some opportunistic schedulers which use the instantaneous channel and queue information can be applied in this level, like the max wait scheduler or log rule scheduler. There are various motivations for slicing. For instance, people may want groups of users under different service providers isolated from each other in the presence of traffic load variations, like in the MVNO service model. It may also be a reasonable choice to group flows based on similar quality of service requirements. So, network slicing is a very useful model with many practical uses, and with no doubt it has gained more and more attention in the recent decades. Here we introduce a general model of the hierarchical structure which we consider in our paper. We assume stochastic packet arrivals for traffic flows, each associated with a queue. And each user experiences random channels as well, which can be observed by the base station. Compared to a classical scheduling model, in network slicing, users first group into S slices, or say S groups. There is a slice-level scheduler, which allocates resources to slices based on some allocation parameter. We call it the weight W. Proper slice-level scheduler can be GPS, the generalized processor sharing, which allocates resources to busy slices proportional to this weight vector. Then we also have flow-level schedulers for every slice. They are pre-selected opportunistic schedulers scheduling users using queue and channel information. And the whole hierarchical scheduler consists of both slice and flow-level schedulers. The way to evaluate this scheduling scheme depends on how we define the utility or rewards. There can be various rewards in application, like minimizing mean delay or rewarding packets to meet specific deadline constraints. In our paper, we do not restrict ourselves to any specific reward scheme, and we want to solve the following general question. What is the best slice-level allocation with respect to the current reward model? In other words, what is the optimal W? With no doubt, this problem is analytically hard to solve due to its complexity. For example, it depends on the traffic and channel conditions, how you do the slicing, what flow-level scheduler you deploy, etc. So what can we do here? We apply a Bandit perspective. Our approach is to model the problem as a black box optimization. We consider the rewards of the system are accumulated over time, and for each allocation vector W, there is a corresponding rate of rewards under the current scheduling and reward model, which we call FW. The ground truth function F and the optimal weight W star, as this picture shows, are unknown to the scheduler in advance due to the complexity of this model. But we can always choose different weights W to run the scheduler and collect feedback, and then try to get an estimation over the function FW. In other words, we are using a bandit. The arms are the weights W, while the feedbacks are how good this hierarchical scheduler performs under different W. Due to the time limit, I will only give a very brief overview of our proposed Bandit algorithm called Chook. This is an optimistic tree search algorithm built from HOO, which is a classical tree search bandit algorithm, with modification to operate on timescale of random queuing cycles. The reason we use random cycles instead of some fixed time interval in this Bandit algorithm is to ensure feedback samples are conditionally independent given the chosen weight in a queuing system. So here's an illustration. Before each cycle, we select one weight to explore the hierarchical scheduler and collect both cycle lengths and reward as feedback. The selection will be adaptively adjusted from all previous cycles, so we switch to another weight for the next cycle. To avoid that the cycle never ends, we also design a clipping mechanism. If you're interested, please refer to our paper for details of the algorithm and more experimental results. So that's all for my presentation. Thank you for your time.